Hello everyone and welcome to my channel. My name is Alessia and today we'll talk about the implementation and applications of Floyd-Warshall's algorithm. Suppose you want to calculate the shortest path between every pair of vertices in a graph, possibly with a tiny program that leaves no space to errors. What will you use? One possible solution is Floyd-Warshall's algorithm. Floyd-Warshall's algorithm uses an adjacency matrix data structure and needs the vertices to be enumerated from 1 to n, with n being the number of vertices of the graph. As you can see, every cell represents an edge. The algorithm uses these numbers to define the length of the shortest path from a vertex to another, using only vertices numbered from 1 to k as possible intermediate vertices. There will be n iterations for every pair, and every time it'll be checked if passing through an intermediate vertex k gives us a shorter path than those previously calculated. In the end, applying the Floyd-Warshall's algorithm to our graph, we'll obtain a matrix containing all the possible paths. We briefly explained how Floyd-Warshall's algorithm works, so let's now see what data structures we'll need. First, we'll need a vertex, which will store the vertex's data, ID, and its edges. Second, we'll need an adjacency matrix, which will store the number of vertices and a matrix called weight, containing all the edges and their weight. Each row I and each column j refers to a vertex ID, and each element of the matrix represents the edge between the nodes I and j. The non-existent edges will be set to infinity, while the edges from one node to itself will be set to 0. Finally, we'll need a matrix that will store all the possible paths. Let's start the implementation defining the vertex class. Next, let's write the adjacency matrix class. It allocates space for the largest possible matrix and keeps track of how many vertices are in the graph. Now, let's develop our algorithm. We'll start initializing the matrix that will store all the paths. Then, we will use three nested loops where k represents the intermediate vertex counter, I and j represent the dimension counters, and the variable through k is used to calculate the distance from I to j passing through k. If no better path was found, we place the direct edge in the paths matrix. And now we return the paths matrix. Next, in order to make our testing easier, let's write a function to get the path from one vertex to another using the paths matrix we previously generated. If there's no possible path, we return none. If there is, we add the starting vertex to a list. We loop through the matrix until we find the ending vertex and we add it to the list. Now, let's write a test class to check that our algorithm returns the correct paths. We'll save our vertices in a dictionary so that our vertices will be mapped to integer from 0 to n. This allows us to fill the adjacency matrix quickly. Okay, let's run it. Excellent! Let's now move on to the time and space complexity analysis through big O notation. We'll start with space complexity analysis. If we exclude the space needed to store the vertices, we just use the adjacency matrix and the paths matrix. Therefore, the space complexity is O of v squared. Now, let's go through the time complexity analysis. The Floyd-Warshall algorithm runs in O of v cubed time, which is asymptotically no better than n calls to Dijkstra's algorithm. However, the loops are so tight and the program so short that it runs better in practice. Let's now list some of Floyd-Warshall's algorithm applications. Suppose you want to start a new business and you need to find the best possible location in relation to the main population centers. Floyd-Warshall's algorithm can be applied to find the vertex that minimizes the average distance to all the other nodes and therefore find the perfect spot for you. Not enough. Imagine you need to know the longest possible time it can take to deliver a letter. In that case, you need to know a graph's diameter, that is, the largest shortest path distance over all pairs of vertices, and can be easily retrieved applying Floyd-Warshall's algorithm. And that's all for today. Thank you for watching. The complete code is available on GitHub, and if you enjoyed the video and want to support me, like the video and subscribe. Ciao!